Hello, this is Group 53, and I am proud to present the Axis ROV. In this video, I'll explain the design process. I first designed the ROV on a piece of paper, and it's super rough, but I had a good image in mind. I like the design because the design helped in distributing the load and its stresses along its stresses, so the body doesn't break with the heavy load conditions applied. So the ROV is almost 2.6 meters long, 2.9 meters wide, and 2 meters high. The ROV has main components like the aluminum chassis, the suspension system, the power system, solar panels, robotic arm, and a claw for that arm, and the camera. So my first motion study is for the wheels. The wheels are coated with silicone rubber that would help the wheels retain their grip with high temperature in Mars. The robotic arm has a degree of freedom of 5, and the claw can rotate with that extra range and precision. There's an antenna addition at the top of the chassis. Next, let's look at the fits and tolerances. While our CAD model fits together perfectly, we need to account for the real-world manufacturing and harsh conditions of Mars. For precision moving parts, like the 100mm camera mast, the solar panel pivot, and the robotic arm joints, we selected an H7/G6 sliding fit. The specific tolerance gives a smooth rotational movement with very minimal play, which is critical for keeping the camera and arm precise. However, for the lower chassis components, like the suspension mounts and the large 148mm wheel axles, we went with a slightly looser H8/7 clearance fit. This extra room is intentional. It accounts for the extreme temperature changes on Mars and prevents the joints from jamming up when exposed to Martian dust and debris. Finally, to ensure the maximum traction without slipping, the wheel hubs don't use a sliding pin at all. Instead, the axles are directly threaded into the wheels using a standard M16 by 2 metric thread, which ensures a secure, locked-in drivetrain system.